Okay. So, before we start digital speech processing, some signal processing concept has to be reviewed, because those will be used frequently in many places. So, you may find difficulty to conceptualize those DSP problem. So, what I do that I will just review some DSP concept, but details I will not go, because details this is a separate subject which is called digital signal processing, because this is the base point of knowing the digital speech processing. So, whatever the acoustic phonetics speech production you know, that is different, because that does not require any DSP concept that much. But once I start explaining the digital speech processing and modeling, discrete time modeling. So, in that cases some DSP concept is required. So, I just quickly go through the some DSP concept. So, what I will discuss, I will not discuss the details mathematics, I will discuss concept behind that DSP algorithm. Okay. So, let us start with that continuous signal. So, if you know that this omega always represent that continuous frequency, this omega. Okay. So, if I say sinusoidal signal, let us A is the amplitude cos omega t plus theta, theta is the phase. Okay. So, this omega is continuous frequency. Okay. Now, what are the property? If you change this, the frequency are distinct, if it is 500 hertz sinusoidal, then the frequency is 500 hertz. If you increase the frequency in time domain, suppose if it is like this, so what you say? Okay, this has an oscillation. So, the number of period in per second give me the frequency. Okay. So, this there is a oscillation is there. Now, if I increase the frequency, what will happen? The number of oscillation or number of period per second will be increases. Okay. So, high frequency means oscillations will be increases. So, that is the property. Okay. So, more period are included in 1 second, more period are included in time. Okay. So, this is the low frequency and this is the high frequency signal. So, this is the concept of analog signal. Now, once I make the digital signal, let us this cos omega t I sampled and stored it as a digital signal. So, if it is a continuous, if x a t is a continuous signal, then what should be the x n? X n is a digital signal. So, x n is nothing but a cos, instead of continuous omega we write this omega n plus theta. This is called discrete frequency. So, this is continuous radian per second, and this is that this frequency is per sample. I will come details, I will come. So, this is written like this way. And what is the property? Now, a discrete time signal is periodic if its frequency f is rational number. What do you understand? What is where the small f is come? Now, what is omega? Omega is nothing but a 2 pi f. Now, if it is digitized signal, what I have done? I have replaced this t by n into capital T. Okay. So, this omega, continuous frequency omega is nothing but a 2 pi f. Okay. So, this frequency is continuous frequency. Now, once I make it discrete frequency, then omega is equal to 2 pi f, but this t is replaced by n t. Okay. So, this omega n becomes, omega n is nothing but a 2 pi f into n into t. So, it is nothing but a 2 pi f into n divided by f s. F s is the, so if the frequency content, let us I write this one, the frequency of this cos this digital signal is 500 hertz. So, let us, this is denoted by f. So, this denoted by capital F. So, f by f s, small f is nothing but a frequency of the signal, that is analog frequency divided by f s. Okay. So, I cannot say that this is a if it is periodic, if this is a rational number, then only it will be periodic. Okay. I am not discussing the number system rational, what is rational number. Okay. Okay. And then discrete time sinusoidal whose frequency are separated by integer multiple of 2 pi are identical. Very simple. If the cos is a distinct sign sinusoidal, if it is integer multiple of 2 pi separated, then they are identical. Okay. So, 2 pi is the maximum period. So, the highest rate of oscillation the highest value of small f. What will be the highest value of small f? Okay. So, f is equal to f by f s. Okay. So, what is f s? As per sampling theorem, f s should be at least twice f. So, I can say f by 2 f. So, it is half. So, in continuous frequency omega can varies from minus infinity to plus infinity. Okay. But if you see this small f can varies from minus half to plus half. Okay. Minus half to plus half. So, if it is f s, if I say that 2 pi capital F is the analog frequency. So, is a continuous signal, omega is radian per second and this omega is radian per sample. So, this can varies from minus infinity to plus infinity. So, this frequency also can varies from minus infinity to plus infinity, but if you see small f can varies only minus half to plus half. And small omega, what is the value of omega? Omega is nothing but a 2 pi f. So, f is nothing but a minus f, minus half to plus half. So, I can say omega can vary only from minus pi to plus pi. Okay, where f s is the sampling frequency. So, omega, small omega represent the discrete frequency and capital omega represent analog frequency. This is radian per second, this is radian per sample, radian per sample and this is radian per second. So, if I say this, sometime this omega is called also normalized frequency. So, if I say I have a signal whose capital F is 50 kilohertz and less sampling frequency is 100 kilohertz. So, what is the value of omega? Omega is nothing but a 2 pi f, where it is 2 pi f by f s. So, it is nothing but a 2 pi 50 divided by 100. So, it is nothing but a pi. Okay. It is nothing but a pi. Okay. Now, if it is 40 kilohertz, then it is 2 pi f into f by f s. So, it is nothing but a 2 pi 40 by 100. So, it is 4 by 5 pi normalized discrete frequency. So, this omega is called discrete frequency. This concept is very important. This will be used in many ways. Okay. So, this omega continuous, this is discrete, this is radian per second, this is radian per sample. Is clear? Okay. Next concept is complex signal. A complex, it is no, everybody knows that complex signal, whether it is a vector, everybody knows a complex vector or complex signal has an amplitude and has a phase. So, I can say if a plus j b is a complex number, it can be written as r e to the power j theta, where r is nothing but a root over of a square plus b square and theta is nothing but a tan inverse b by a. Same things, a complex signal. Okay. Now, I come to the impulse representation. So, suppose this is given, x n is represented by x k and delta function. Okay. So, n minus k. So, if I say this my p n is like this, let us p n is my digital signal, p n is a 3 delta n plus 3. Okay. Plus a 1 delta n minus 1 plus a 2 let us delta n minus 2. So, this del a 3 a 1 are the coefficient and those are the delta position. So, at that position the signal has amplitude a 3, sample has amplitude a 3, at that position signal has amplitude a 1. So, that can be represented like this way, because it is plus 3. So, minus 3 point there will be a sample whose coefficient amplitude is minus a 3, there is a sample at first sample position 1, 2, like that way it is represented. Okay. So, this is the impulse representation of a sequence. So, if I say I have a speech signal x n who has, suppose that is a 100 sample. Okay. Now, if I say the sample start from 0, 1 to 100, then first sample is nothing but the amplitude less first sample amplitude is a 1 with delta n, n plus n minus 0 is 0, next a 2 delta n minus 1, like that way I can write. Okay. So, that will be used in different time when you process the digital signal. Okay. Now, next concept is classification of signal, different type of signal, energy signal, power signal. I am not describing, you know that if it is energy infinite then called energy signal, if power is finite then it is called power signal. Periodic signal, aperiodic signal, a signal is periodic if it is repeat its nature after certain time interval in time domain. If it is repeat in nature, let us after n sample, then I can say the n sample is the period of the signal. So, x n is periodic with period n if and only if x n plus n is equal to x n. So, what is the periodicity? If this point and next repeating point if same, then I can say the signal is repeat itself. So, it is the period. Okay. So, digital signal x, if n is the period, then x of n plus small n plus capital N is equal to x n, then you call signal is periodic. Then symmetric and antisymmetric signal, a real valued signal x n is called symmetric if x of minus n is equal to x n. Okay. On the other hand, if it is antisymmetric, then x of minus n will be minus x n. So, this is a signal property. Next, discrete time system. So, signal periodic, aperiodic, signal symmetric, antisymmetric. I have not discussed. Signal is called stationary and non-stationary signal is also. So, what do you mean by stationary signal? If the signal does not change its property over the time, then I can say it is a stationary signal. Suppose I have a sinusoidal of 500 hertz, this is a 500 hertz sinusoidal. If I take this time, all the time it is 500 hertz sinusoidal. So, I can say the signal is a stationary signal, it does not change its property along the time. Now, say the speech signal. If I say speech signal, if I say a sentence, along the time the signal properties varies, sometime it is silent, sometime it is voice, sometime it is silent, sometime it is friction, then maybe silence, then maybe voice. So, I can say along the time signal changes its property. So, it is a time varying signal. Okay. Later on you learn that signal processing algorithms are applied on a stationary signal. So, I have to consider how I make the speech signal is non-stationary. So, those kind of consideration we will take. Okay. So, this is stationary and non-stationary signal. Then I come to the systems. If you come system, this is called discrete systems. I am not going to the analog system, you know the signals and systems, that class. So, discrete system, let us output of a discrete system is y n is nothing but a h of input x n. Okay. So, h is the transfer function of the systems. Okay. Let us the system is like this, y n is equal to 0.8 y n minus 1 plus 0.5 x n plus 0.9 x n minus 1. So, if I told you draw the system diagram, digital system diagram. So, I can say what is y n minus 1 means the y n is delayed by sample number 1, the sample 1 sample, n minus 1 means 1 sample delay, x n minus 1 means input is 1 sample delay. So, if this is my x n, this is my x n. Okay. So, x n has to be multiplied with amplitude 0.5 and has to be added with 0.9 multiply x n minus 1. So, I can say let us I take one x n in here input and apply a z to the power minus 1 delay. Z to the power minus 1 represent one sample delay and added with this signal with a amplitude of 0.9. So, output is nothing but a 0.5 x of n plus 0.9 x of n minus 1. Okay. Now, this is my y n. So, y n is nothing but a this plus there is a y n minus 1. So, I can take one input from here and then z to the power minus 1 delay apply and added with it with a multiplication factor. So, this is my system diagram. So, this is y n and this is x n. So, signal flow is this way, this way, okay or not. Okay. So, discrete system can be implemented like this way. So, z to the power minus 1 is nothing but a single sample display. Now, a system consists of certain properties. I will come implementation later on also. A system has certain property. What are the property? It is maybe statics or it may be dynamic system. A discrete system is called statics or memoryless if its output at any instant n depend at most on the input sample at the same time, but not past or future sample of the input. So, suppose my y n is only depends on x n and x n minus 1, but not x n plus 1, then I can say my system is static. Okay. So, or memory less system, and if it is future sample, then I can say it is with memory system. Okay. So, memory less system, static system, with memory system is dynamic system. Then time invariant and time variant system. Time invariant and time variant signal, that is called stationary and non-stationary signal, but if it is time variant and time invariant system. So, if the system does not change its property over the time, then I call it is a time invariant system. If it is changed along with the time, then I can say it is a time variant system. If I consider this vocal tract is a system, along the time it change its construction. So, it is a time varying system. Suppose suppose operator square, always it will be square, whatever the input will come, it will square. So, property does not change along with the time. So, it is a time invariant system. So, how do you mathematically say that? If it is x n is the input of a system H and output is y n, if I apply x n minus k, I should get the y n minus k, then it is called time invariant system. Along the time, system does not change its property. Okay. Now, linear and non-linear system. So, how to test the linearity of the system? The system is linear if it is suppose the superposition principle. So, what is superposition principle? If you know that if I apply a two input x 1 n plus x 2 n to a system H, whatever output I will get, this will be same if I apply two input individually. Let us put a factor a 1 and a 2, this a 1 x 1 n plus h of a 2 x 2 n. So, if it is support the superposition principle, then I say the system is a linear system. So, if the system is linear and time invariant, then we called LTI system, linear time invariant system, that is called LTI system. That means, the system is linear, system does not change its property along the time. Okay. Then you know causal and non-causal system. So, if it is not depends on the future, then I call system is a causal system, means y n is only depends on either x n or x n minus 1, but not the future input, future input will be x n plus 1. If it is not depend on x n plus 1, then I call it is a causal system. If it is depend, then you call non-causal system. Then stable system, unstable system. What is stability? If I apply a bounded input to the system, it should produce bounded output. If I apply a bounded input, if the system produce bounded output, then I call the system is stable system. BIBO, bounded input, bounded output. In bounded input should produce bounded output. Okay. Then stable and unstable system. Then there is a recursive and non-recursive system, that you know, that this slide is self-explanatory, that explaining that recursive. If the output depends on the previous output, then we call it is a recursive system. Okay. I am not describing details. Then very much, or you can say the most commonly used signal processing algorithm in speech is called convolution. Convolution. So, convolution is the most frequently used. If you see that if I want to find out a output for a input in a system, then the system transfer function is convolved with the input to produce the output of the system. So, convolution is most commonly used algorithm in DSP. Okay. So, suppose yn is produced using a system property hn convolved with input xn. Okay. So, how the mathematically it is written? It is k equal to minus infinity to infinity h of k into x of n minus k. So, yn is equal to h of k into x n minus k of yn. Okay. So, convolution means that suppose this is my system and I apply a signal here. So, output is the property of the system must be convolved or modify the input signal produce the output. Okay. So, each property of the, you can say that whole property of the system should modify the each input of the signal. So, that is why whole hk will modify the each input. Okay. So, this is convolution. How it is done? It has a operation, or how many operation is involved? It is folding, shifting, multiplication and summation. If you look at this equation, it is nothing but a folding. So, if I say x n equal to y equal to 0, then it is nothing but a h k multiply x minus k. So, I can say the x k is folded to produce x minus k. Okay. So, I can give you an example. So, this is my signal and this has to be convolved with this. So, green is the system. So, sorry, there is a wrong interpretation. You can say that this is h and this is x. Let us same things consider, this is h and this is x. So, I can say this h is convolved, or you can say the x property of x is convolved with h t. So, what I said that h has to be shifted, folded. So, y t is means h has to be folded first, folding, then shifting t equal to 0, then product and sum, this sample product with this sample produce sample, then shift the singlet by t equal to 1, then again product and sum, then again t equal to 2 product and sum, then again one sample shift product and sum. So, that way output will be produced. Let us give an example. Let us xn is nothing but instead of writing that way, let us 1 1 1 and here let us this is 0 0 1 2 3 and let us hn is nothing but a 1 1 1 and here. I am not giving the same example which is in the slide. Okay. This is two signal. So, what is there? Hn So, x n I want to produce y n, which is nothing but a summation of k equal to minus infinity to infinity h k multiply by x of n minus k. So, which signal has to be folded? X n. So, I can fold the x n. So, if I draw in spectrogram, so this is x n, first sample, second sample, third sample, fourth sample. So, 0, 1, 2, 3, 0, 1, 2, 3. So, if I want to fold it, so it will be this side 1, 2, 3, and if I want to plot h n, it is nothing but a 1, 2, 3. So, my y n, first I fold it, multiply by 0. So, y 0 is nothing but a multiply by this or this with this. So, 1 multiply by 1 and this with multiply by this 0. So, this is 0, this is 0, this is also 0, this is 0, sorry, this is y n. Okay, I will draw freshly. So, it will be just let us draw it neatly. So, use this pen. Okay. So, this is my x of n, sample number 1, sample number 1, 2, 3 and 4, and this is my h n. H n is nothing but a sample number 1, sample number 2, sample number 3 sample is there. Okay. Now, what I said, to produce the convolution, I draw the first. So, produce the convolution, x n has to be folded. So, I folded x n, I will draw here to here, this is number 1. So, folding is this side 2, 3, let us 4, I folded it, and so this is x of minus k. Now, I use the h k, is nothing but a 1, second sample, third sample. So, this is h k. Okay. Now, what is my y? So, this is let us y n. So, at y 0, this multiply this, and if I say this side, if I projected this side, it is 0, here it is also 0, here it is also 0, here it is 0. So, here also it is 0. So, product this multiply with this, sum with this multiply with this, sum with this will multiply with this. So, 0 into 1 plus 0 into 1 plus 0 into 1 plus 1 into 1 plus 0 1 into 0, like that way it will come. Okay, this will multiply with this, add, and so I can get first sample y. To get the second y n, what I will do, instead of doing here, I shifted this signal one sample. So, what I can say, let us shift this. So, this will be first sample, this is the second sample, this will be the third sample, 1, 2, 3, 4. So, this sample again become 0. Now, I product this will this, 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 and add together and get the y n. So, that way I get whole y n. So, that is why folding, shifting, product and sum, the convolution. Okay. Then there is a term called circular convolution. Circular convolution of x n and h n is defined as the convolution of h n with a periodic signal x p n. If the signal is periodic, then I can do a circular convolution. Okay. So, this is the mathematics. I am not going details of the circular convolution. Okay. Next, correlation. Correlation is similar mathematics with the convolution. What I want? Suppose I want to find out there is a signal like this and there is a signal like this. I want to find out whether they are similar or not. So, that is why it is called correlation, relation between, let us this is x n and this is y n, or you can say this is x 1 n. So, correlation between x n and x 1 n is nothing but a similarity between these two signals. How do I find out? I just take the, so it is a digital signal. So, I take the sample by sample, I take the sample by sample. So, I can say that I can multiply the two sample and then take the sum, product and sum is the correlation. So, I can say the first correlation coefficient, or I can say Lth correlation coefficient R L is nothing but a product and sum n equal to minus infinity to infinity x n with x 1 n minus L, or x n with n plus L, x 1 n plus L. So, it does not matter whether I shifted the signal this way or this way, both will give me the correlation. Okay. So, this is the Lth correlation. If it is 0th coefficient, then I start from 0 sample to 0 sample. If it is 5th sample, then I shifted this signal this side 5th sample. So, start with this portion of the signal will be not used. So, I will compare this portion signal with this whole signal, understand. Then if I did L equal to 10, then let us, this is the 10th sample. So, this portion of the signal is deducted and I compare this portion with whole signal. So, that is the correlation. Okay. So, details, there may be a detailed discussion in signal processing books, you can refer to any signal processing book. The algorithm also I have written down, you can go through the slides and find out that things, then the convolution correlation. So, then LTI discrete time system, which I have to consider, because in signal processing or digital speech processing, we consider that this production system is an LTI system, discrete time, linear time invariant discrete system, LTI discrete system, linear time invariant, linear system is linear, system is time invariant and a discrete system. Okay. So, linearity you know, time invariant no, and LTI impulse response is direct convolution. I am not going details. Then why I take that LTI system? Because it is easy to understand, it is easy to manipulate, powerful processing capability characterized completely by their response to unit sample via convolution relationship, basis of linear filtering, use model for speech production, use as a model for speech production. So, always we try to model this one in a LTI system, because it is easy to understand, signal processing respect, it is easy to understand, it is easy to manipulate, it powerful processing capability. So, that is why we always use LTI system, linear time invariant system. So, we want to make this model as a LTI system, linear time invariant systems. Okay. Now, if you, this is the same signals and system, you already you have read it. If the x n is the input, h 1 and h 2 are the two system functions, the transfer function, and y n is the output, then it is a it is commutative. H 2 can be first and y n can be the second also. Okay. So, all those property you know that. Okay. This is parallel, I can shift it here and here. So, I can plus it or I can star it. Okay. So, this is a review of the system property. Then I can ask you that draw the transfer function of this one. So, these two are parallel, this is series with these two system, and then again this the whole transfer function will be parallel. Okay. You can practice it. Now, implementation is important. So, how do you implement a discrete system? There is two kinds of implementation, one is called direct from 1 and one is called direct from 2. So, one is called structure 1 implementation, another is called structure 2 implementation. So, what I said, suppose y n is nothing but a 1 y n minus 1 plus a let us b 1 x of n. This is my system. This can be a system. So, I can write down the system, this is my x n input, and I can say that x n n minus 1, let us it is n minus 1 plus let us c 1 into x n. Okay. So, I can say this is multiplied by c 1 added with a delay sample z to the power minus 1 and multiply by b 1. Then output is y n is nothing but a delay sample, which is z to the power minus 1 y n minus 1 multiply by a 1, this is multiply by a 1 added with this input. So, this is the implementation of that system. Now, I said that if a system has, this is my input x n and a system had h 1, then I have another system called h 2, this is h 2 and this is y n, then I can interchange these two systems, h 2 can be here and h 1 can be here, does not affect that output. So, I can say I can change this side to this side and this side to this side. So, I invert that one. So, I can say x n inverting it. Okay. So, I can say x n plus this one is coming this side plus a 1 z to the power minus 1, then this side coming this side z to the power minus 1 plus b 1. So, this is c 1 will be there. So, this is called direct form 1, because there is required two memory, two delay are separate, input delay and output delay are separate. If I implement this way, then this signal is same. So, I can say instead of two delay, I can replicate it by a single delay, z to the power minus 1 multiply a 1 and z to the power minus 1 multiply by b 1, and this is c 1 will be there, x n input, y n output. So, this is the advantage. This is called direct form 1 and this is called direct form 2 implementation. Okay. So, DSP book it is there. This is I said that in long, this is one block and this is block, once you interchange it will come same side. So, instead of 2 z to the power delay, I can club together and put a single delay. So, it is called direct form 2 implementation. Okay. We use this thing when we implement these are vocal cord systems using discrete time systems. Okay. Okay. So, next class I will just complete this DSP things. Okay. Okay. Thank you.